Fundamental theorem of calculus. We've looked at the antiderivative and the area problem. We've looked at the derivatives, which is the tangent problem. Well, there's a close connection between these two somewhat seemingly unrelated operations. For the most part, differentiation and the definite integral are inverse operations in the same way that division and multiplication are inverse operations. We've been using the integral sign to denote the antiderivative, which gives you a family of functions, your indefinite integral. But a definite integral, the one that we've been using for area, gives us a number, and that's denoted over here. Well, for the most part, you can do your antiderivative of your function, that's what capital F is, plug in b, your upper limit, and then subtract what you get when you plug in a, your lower limit. And that's for the most part how you're going to find area, and that's what the fundamental theorem of calculus says. And that's what it's saying here. It says f, capital F is your antiderivative, plug in b minus plug in your lower limit of a. Now we don't really need to include the c here because when you look down below here, if we did that, we would go ahead and plug in or work out this, and that would be this right here. We would then come back and we would work this out, which is technically this. But when you distribute through your negative sign here, your c's end up dropping. So when you're dealing with a definite integral, you do not need to be concerned about these c. So to evaluate these, you're going to do your antiderivative of the x squared. Get this. Then you're going to evaluate it from a 3 to a 0. So that means you're going to take 3, plug it in here, and that's what we have, the 1/3 3 cubed, minus what you get when you plug in your 0. So you're going to get a 27 times 1/3, which is 9, minus your 0, so you get 9 for your answer. So the area underneath your curve of x squared between 0 and 3, which is denoted down here in your graph, is just 9. Same idea over here. We have our sine curve between 0 and pi. So we got to do our antiderivative of sine, which is cosine, or negative cosine, and then we got to integrate or evaluate that from 0 to pi. So you plug in pi, it's the opposite, plug in pi, minus opposite of what you get when you plug in 0. So you get 1 plus 1, which is 2. So the area underneath your sine function between 0 and pi, which is an irrational number, ends up just being nice, neat, normal 2. Here, same process, do your antiderivative. X squared is your antiderivative of 2x. Here you got to increase your exponent by 1, so you're going to get an x to the 1/2. But then you got to think, okay, I don't have a 1/2 in front, so what would undo that 1/2 power? So that means I got to have a 2 in front. Because if you take the derivative of this, you need to get what we have above. Then we got to go ahead and do the 3. So then you're going to plug in your 9, subtract what you get when you plug in your 1, and you get 52. Same idea over here. You're going to have to increase your exponent by 1, which will be a 4. But that means you got to have a 1/4 in front to undo that because there's no 4 in front. But remember, you got to also undo your chain rule. Your chain rule would say you'd have to multiply it by 2. So you got to undo that multiplying by 2. So that's why there's a 1/2 in front. So really it's just a 1/8 in front. Plug in your 1, plug in your 0, subtract, differentiate, or subtract them, get 10. So for your original problem here, the area underneath this curve shaded down here in blue is just plain old nice normal 10. Now, with this one here, when you're dealing with a root, you may want to go ahead and rewrite that so you're dealing with a fractional exponent first. Being a 1/2, so that means you got to increase your exponent to your 3/2. Your 3/2 is here, so to undo that when it comes down front to take your derivative, which we do have over there, you got to have a 2/3 to undo your 3/2. We have a 1/3 here because that's got to undo the chain rule of the derivative of the inside, which is 3. So a little bit of simplification. Plug in your 5 minus what you get when you plug in your 1. And so we get 112/9. That's the area shaded in over in blue. When you're dealing with absolute value, you got to once again do a piecewise just like we did for a derivative. You got to think, okay, sometimes my absolute value is going to do nothing. Sometimes my absolute value is going to put a negative sign in there because you got to take the opposite of a negative to make it positive. Well, for what values of x would this be positive or not change? And that's when you're dealing with 0 to 3. However, if you're dealing something between -1 and 0, it does the opposite of that. So it's going to be a negative here. So now, really all you have to do is do the integral of the first one plus the integral of the second one on the appropriate domain of each function. You do your antiderivative and evaluate each one, and you just end up with 10. That's what you do with absolute value. However, in the context of our graph over here, we could just do the area of the big triangle, area of the small triangle, add them together. Either way, you're going to get the same answer. The mean value theorem. The right side says, it has to be continuous. Says the right side is really just the area underneath your curve. That's the pink area. What we have over here is just the area of a rectangle. Rectangle has to have the same width from B to A. That's what this is saying. So we have a rectangle of the same width, but now we got to figure out what is that height, and we're calling that f of c. So that height, which is really your average height, which we're talking about down here, it's just saying that average height will intersect your graph somewhere in between A and B. That's what the mean value theorem is saying. The average value theorem is saying, okay, let's take this right here, get the f of c by itself, that's your y value, your average y value. So to get rid of this, we got to go ahead and divide both sides by it or multiply by the reciprocal. Your average value is really just the average height of your whole function if it were a rectangle, instead of a curve in which your curve and your rectangle would have the same area. So let's go ahead and find your average value of this. Here's your average value. In the context of this problem, we're going from 5 back to 2. So we're going to integrate from 5 to 2 of your function, because we're trying to figure out the average temperature at Athens, Georgia. Well, you know your 5 minus 2 is this. You got to go ahead and do your integration here. Increase your exponent by 1. Okay, cosine, you know you're going to have that 18 hanging around. You know you're going to get a sine of this, but you might be wondering, well, where does this come from? Well, remember, you got to undo the chain rule, which would say the derivative of sine, which you know is cosine, times the derivative of the inside. So you got to undo that pi over 6. So then you got to evaluate that from 5 to 2. So you come up here, you plug in your 5. You go back up there, you plug in your 2. Subtract your 2 answers. Multiply that by 1/3. You get something very close to 57 degrees Fahrenheit.